In this video, we're going to be looking at two trends. The first trend that we're going to be looking at is the radius of an atom. And then the second trend we're going to be looking at is the ionization energy. So I have this prompt right here, and it says magnesium has a radius of 1.41 angstroms, silicon has a radius of 1.11 angstroms, and calcium has a radius of 1.67 angstroms. Explain why this trend is observed. So if we go ahead and we kind of point out where these are, because it's always important that when you're looking at these problems that you identify where they are on the periodic table, because where they are on the periodic table will help us to rationalize their trends. So if you can't see it, I have one right here, and one over here. So we're going to be rationalizing each one of these. Now, if you look at where they are, I'm going to also rank these from the largest to the smallest. So this one is calcium is 1, magnesium is 2, and silicon is the smallest. So if we were to identify just the trend that we see on the periodic table, what we would see is that going from left to right across the periodic table, if we compare magnesium to silicon, is that the atomic radius actually decreases. And when we go down a group, we see that the atomic radius actually increases. So what we're going to do is we're going to kind of rationalize why we observe this trend. So let's first start off with comparing magnesium versus silicon. So if you look at these, what you see is that they are in the same period. And if you have them in the same period, what you really want to focus on is the number of protons that each element has. So when we look at this, what we see is that magnesium actually has 12 protons, while silicon has 14 protons. What does this mean as far as atomic radius? Well, the more protons you have, the stronger the attraction to the nucleus. So what's going to end up happening is that those electrons, which they're all in the same period, so they are not that far away from each other, the one with the more protons is going to be holding those electrons a little bit closer. And when they hold them a little bit closer, the radius gets smaller. So when you're looking at this in the same period, you're going to be focusing on the number of protons. That's going to be why you observe the trend that you do. Let's switch gears and let's look at the difference between magnesium versus calcium. Yes, magnesium and calcium do have different number of protons, but when you're comparing them and they're in the same group, what you're going to be really focusing on is the subshell for the electrons, because that's going to tell you how far those electrons are. So if we look at this and we look at where magnesium is, what we see is that magnesium is in the, let's see, that would be our 1, 2, 3, our 3s subshell, versus calcium, which is in our 4s subshell. Well, that 4s subshell is further away from the nucleus. And if it's further away from the nucleus, that means that my radius is larger. So when we're comparing this, again, what we're looking for if they're in the same group is we're going to be paying attention to the subshell that they're in, because that's going to tell us how far away those electrons are. So let's switch gears a little bit and let's look at this next kind of prompt. And what we're going to do is we're going to rank magnesium, silicon, and calcium from the lowest to highest ionization energy. And we're going to explain why we observe this trend. So when we do this, we're going to kind of take a similar approach. And what we will see is that the trend is actually opposite of atomic radius. So if I go back up to this periodic table that I had up here, and I were to draw it in, I'm going to go ahead and draw it in with my blue pen. Ionization energy, and I'm going to abbreviate this by saying IE, actually increases from left to right and decreases down a column. So going back to this, let's go ahead and kind of observe this trend and explain it. So if I were to rank these, what's going to happen is that if it's the opposite, since silicon had the smallest ionization energy, that means the smallest radius, that means it's going to have the largest ionization energy. And calcium had the largest radius, so it's going to have the smallest ionization energy. So it's going to be calcium, and then it's going to be magnesium, and then it's going to be silicon. Now, in case you guys don't remember from our notes that we've already taken in class, let's make sure that we understand what ionization energy is, because understanding what that is going to help us explain why we observe the trend. So ionization energy is the energy required to remove an electron. And if that electron is held really close to the nucleus, the attraction is greater, so it's going to be harder to remove. So let's think about this. Calcium, which has the largest radius, let me respell that, has the largest radius, has the lowest ionization energy, and I'm going to abbreviate ionization energy by just putting IE, and that's because those electrons are not as close to the nucleus, so the attraction is weaker, and electrons are easier to remove. We can also do the exact same thing, but kind of the opposite with silicon. So let's go ahead and rationalize the one that has the largest atomic radius. The largest ionization energy. So silicon has the smallest radius. And because it has the smallest radius, the electrons experience a stronger attraction to the nucleus. And because they experience this stronger attraction, they are more difficult to remove. And if they're more difficult to remove, the ionization energy is higher. So notice that I can explain ionization energy in terms of atomic radius, because atomic radius does lend itself to explaining why it's hard to remove an electron. Why it's hard to remove an electron has to do with how close those electrons are to the nucleus. The closer those outer electrons are to the nucleus, the greater the attraction, the harder they're going to be to remove. If those electrons are really far away from the nucleus, they're not held as tight, or they're not held as tightly to the center, and so they're going to be a lot easier to remove, so not as much energy is going to be required.